today we are going for that is HAMQ learning will be there. What is HAMQ learning is there? That is hierarchy of abstract machines are there that we are using today. And basically that is if you have been studied that theory of computation, automata and other things will be there. And C++ things will be came in that HAMQ. Other things will be came. So this HAMQ learning, and in other terms we will say that HAM, that is approach to HRL. HRL means hierarchical reinforcement learning. In it, the designer specifies abstract actions by providing stochastic finite state automata called abstract machines that works jointly with the MDP. Okay. Next, this approach is basically explicitly specify abstract of actions following users to provide background knowledge more generally in the form of partial programs with various level of expressivity. What that means, just like in C++, we are creating that classes are there, and within that class we are creating that objects will be there. With the help of objects we are getting that functions, and these things will be there. Same thing we are using, but here we are using in terms of abstractions and other things. Okay. In abstract machines, we are having that three things will be there. Mu will be there, L will be there, and delta will be there. Where what will be the mu will be doing? Mu is a finite set of machine states, and L is a stochastic function will be there from states of MDP to machine states that determine the initial machine state. And delta, what is the delta? Delta is a stochastic next state function that is mapping machine for states and MDP state to the next machine state. So these three terms we are using, mu, L and delta we are using in it. And it was having that two types of the different machine states are of two type of this will be there. First is the action state, and secondly we are going for the call state. In action state, it specifies the action to be taken given the state of MDP to be solved. What will be the call states? Call state means it execute other machines as a subroutine. That is the important thing, as a subroutine. Choice states non-deterministically select the next machine state. Hold state will be there. There will be another state will be there. Hold state will be there. And hold state means hold the machine. So these three things we are using in it. Then here in that HAMQ, we are having that using with the help of an example, we are clearing. So first we are having initially the choose state will be there. We are having that two ways will be there. One is this side and one is this side. If we are leaving this side, so what happened? We are leaving room to the north side. If we are leaving this side, then we are leaving to the room from the west side. Now what happened if we are leaving from the west? So in west also we are having that three different directions will be there. One is north, one is south, and one is itself the west will be there. So now what happened if we are going to this direction? So we are having all three options will be there. That is the north, south, and west will be there. From north, this is the basically this is the point where that all extractions will be going on there. So in that point, we are that is your known as that circle will be there. On that point, we will just go through it, and we will again reach from that particular point to this thing. But that is only for that checking out the different options that will be west wall, south wall, and north wall. What will be there? That will be going on there. But if you want to go to door, then we are having only that one way will be there. That is this door will be there. That directly go to the choose. Now, same thing, whatever we have been go through this side, and same thing will be going on for this side also. Same thing, it was east, west, and north will be there, and we are having that north will be there. We are having some this weightage have been defined, and if you want to go for this one, then this will be there. So this is that our HAMQ learning will be there, where we are using with the help of this example, the abstract level of this hierarchical we are going to conduct. Next one. Then next one will be, we are using MAXQ. What will be the next one? Next one will be the MAXQ will be there. MAXQ is an approach to HRL, hierarchical reinforcement learning, where the value function is decomposed over the hierarchy. What will be the main thing? We are having a value function that is decomposed over the task hierarchy. It can be lead to a compact representation of value function and make subtask context free or the portable. That is the important thing. It can lead a compact representation of a value function and make the subtask for the context free or the portable. In MAXQ, what happened? The abstract actions are crafted by classifying subtask terminal states as either goal state or the non-goal state. So these things, three, they have been bifurcated in MAXQ. So using distinctives for non-goal state, policies are learned for each subtask to encourage termination in the goal state. This termination predictive method may introduce an additional source of suboptimality in the MDP. We are saying the pseudo reward can be disordered subtotal. What that means, that this is the way of that things, how that we are having that going for that the terminal state, a goal state and non-goal state, how that non-goal states and predictive and this will be using. So that will be there. A key feature will be there, that the value of state as a decomposed of subtask means if you are having that will be a main problem will be there, main task is there. So we are having that so bifurcated that all these tasks will be like that. But when we are merging these all subtasks, so it will be came for the solution of this task. So that all these things will be subtask and this will be going on. A complete value is expected. This continues a communicative reward to complete the subtask after the next abstraction action. What happened on the basis of these tasks? What happened? We are having that separate states will be there, as well as actions will be there. Abstract actions will be there. On the basis of how they are dealing with that each and other thing, that will be discussed in MAXQ. So here that we are having that this algorithm will be there. So we have required V, M, and S will be there. Primitive actions of M will be there, and A is having that actions will be there, and C will be there. M, S, J will be there for all J belongs to AM. If F if M is an primitive action, then what we are having, we will return this one, just like we are having now. We are having that what we are getting, we are having that new state we are getting now on the basis of actions will be there. Here what happened, we are having V will be there, and inside V we are having M and S will be there, and M we are getting from this one. So that will be there. Else what we are doing, for each J we are going for that that belongs to this thing, unless we will evaluate this thing, and we are using here the greedy algorithm. From the greedy algorithm, we are just using this one, and this will be going on there. So how this thing will be, this is that basically MAXQ just algorithm will be there, how that this will be required and how it will be working there. And now that the introduction of max operator means that we have to complete search through all the parts in the task hierarchy to determine the best action. Algorithm forms such as the depth first search and return both the values and best actions for subtask M in state S. Okay, so same example that we have been discussing the previously, that if we will, our agent will be there. So agent is performing that what action, if he was going to there, this side wall will become, so he will be there. He will be there. Here it was some actions will be going on. Here it also some going for some actions, but this is the appropriate that we want, that this is the goal state. Now, this is the algorithm, how this thing will be going on. You just go through this algorithm. I will share this algorithm with you. You just use it with the help of program, then you can understand. Then we are having the task hierarchy of the 4-room task will be there. So we are having that that will be initial room is there, and this is that your agent will be there, and this is that our exit door will be there. So how we are doing there? The agent can leave each room. One of the potential doorways will be there. To the north, what will be that there? To the north, east, south, or west. We are having these things will be there. Na? Either you can go to north, east, west, south will be there. So, and we need to learn a separate navigation strategy for each. However, because the rooms are identical, the room variable is relevant for intra-room navigation. So that we have already task hierarchy for room task we have already discussed. Same example, you can just go ahead with them. Then we are having evolutionary computation for reinforcement learning. In evolutionary computation for reinforcement learning, we are starting with that this introduction. Algorithm for evolutionary computation, which simulate the process of natural selection to solve the optimization problems in an effective in an effective tool for discovering high performance reinforcement learning policies. So that is the important high performance reinforcement learning policies that we are getting from there, because they can automatically find good representation, handle continuously each action space, cope with partial observability reinforcement learning approaches, which are having that empirical record, sometimes significantly outperforming. So these are that why we are using this one. That is the answer of why. Then this is an application of evolutionary computation of reinforcement learning, overviewing methods for evolving neural network topologies. For why we are using? Because we want to determine that neural network topologies there and their weights. Hybrid methods are there. Also they are using temporal difference methods for evolutionary method, and we are using for multi-agent settings will be there and generating their development, and we are also used for online evolutionary reinforcement learning. So here we are in that this one introduction of evolutionary computing universal algorithm. First, we are having that simple reinforcement learning will be there. After that, we are going for neural network topologies will be there. Then we are having the temporal difference will be there. Then multi-agent we are using, and we are using that online environment for the reinforcement learning will be there. So that is the evolution of that where from where they have been started and up to what point they will go through. Okay, right? Then we are having that another type will be there. Genetic algorithms will be there. Algorithm for evolutionary computations, sometimes known as the genetic algorithms will be there. They are optimized methods that simulate the process of natural selection to find that is highly fit solutions for a given problem. Typically that we are assuming that the fitness function we have already studied. This is the fitness function will be there, that will be map, and it was going for the real value, and the measure of fitness will be going on. You will go through that previous lecture when we are going for fitness and how we can find that. We have already discussed same thing. We are going for this thing, and we are having this one for that we are using for the same. Then evolutionary method basically search for C asterisk by representing, selecting, and reproducing a population of a particular candidate solutions. The initial population is typically chosen randomly anywhere from that. If this is the population will be there, anything we will be pick up to choose. After which each member of the population is evaluated using F, and the best performing ones are selected as the basis of a new population. This new population is found by how that is performed. It is found by the reproduction, in which the selected policies are mated. That is, your components of two different solutions are combined and muted. That is, the parameter values of one solution are statistically altered. That is that how we are getting that this new population, and how that new population will be going to go ahead. So this process repeats over many iterations until sufficiently fit solutions have been found or available of computational sources have been existed. There are numerous number of variations of this approach, such as multi-objective methods, diversing algorithms, and distribution-based methods will be there. However, the basic approach is extremely general, can in principle be applied to all optimized problems, which F can be that you have been specified. You know now what will be the F will be there, because we want to get that new population and this thing, how we are getting with the help of this F. Then evolutionary methods do not use the fact that the policy they can searching for a function form from the states to actions. They do not notice which state an individual passes through during its lifetime or which action is it selects. In some cases, this information can be misleading. Example, when states are perceived will be there, but more than we have, that is not an important point. Just consider only these two. Then we are having the Neuro evolution will be there. That is basically we are having that we are using for neural networks. No, we have already discussed about this one there. Neural reinforcement learning. So now we are going for neural network. That was HAMQ in 1994. They will be introduced. They are extremely general purpose way for representing that our complex functions will be going on there. And because of this consistency, they are popular representations for reinforcement learning policies, not only for that, not only specific for the evolutionary computations, but it also for that other policies such algorithms and for other distemporal difference methods. This section particular introduces the basic that what will be the neuro evolutionary approaches will be there to reinforcement learning, in which evolutionary methods are used to optimize that neural network policy. That is the important. Then we are having the neuro evolution will be there. We are having illustrate the basic steps how that neuro evolutionary algorithm will be going on. In each generation, each network, the population is evaluated as a task. So next, the best performance performing our like example, by rank based selection we can go ahead, or by that wheel selection we will use, or tournament selection. There are various ways that how we can just select that the another this one. What we can say that is an algorithm for the next generation and whatever F we have been calculated. And whatever the selected networks will be there, they are crossover and mutation and reproduce to form a new population, and the process repeats unless. So this will be that step one will be there. First we are evaluating will be there. Step two, whatever that this one next the best performing are selected. Example that we are using Y, that rank based selection, root wheel selection, tournament selection, that we are going in that second step. After that, what happened? We breed that new population. How we are breeding? We are breeding through that crossover and mutation process. Then what happened? We are getting that new population. We are having that here, that new population will be there. And we are repeating these all steps unless what happened to form a new population, and we are repeat for this selected networks for that up to that we are not getting that that output for the same. So this is the neuro evolution. In a reinforcement learning setting, each input node in a network typically corresponds particular state features will be there, such as the value of the input together describe that agent state. There are many other ways, many ways to represent actions. If action can also be described with features, as is common with continuous action spaces, then each output node correspond to an action feature. Okay, whatever the action we have been taking, the specific action is having some features, and that corresponding features will be used. In this case, the value of the output together describe the action will be selected of that given state. What happened? We are having already discussed this one. If we are having a function of that particular that we have taken that example of that class will be there. No? In that class, we want that top 5 student in that particular 5 exam that will be there. Top 5 student in the class. So we are having first, we are going for that calculating that first sessional, second sessional, third sessional marks. So that example, same example, we will be used for here for the neuro evolution. Where the number of actions is small and discrete, a separate network can be used for each action. That is the common value function approximation. If that is small task, then we are going for it this way. In this case, each network has only that one output node will be there, and the policy action for a given state that corresponds to the network that produces the largest output for the state. That is the another case that we are dealing for the same. Then this will be the algorithm will be there. So S is the set of all states will be there. A will be the set of all actions will be there. P will be the population stage will be there. G will be the number of generations will be there. And E will be the episodes per generation will be there. This is first point. What we are creating a new population P with an random network. Then we are going for that this one we are doing with this one for these things, and then from this state we are selecting that selected from the next network. Then we evaluate from this evaluate selected network, or the current state will be there. Then the selection action, which highest activation will be going on there. Then we are going to take action and transition for the new state. After that, we are update the total reward by n, and again that if the update the total number of episodes for new, and the new arrow will be taken and make a new network base for fit. You can create this algorithm in your language also. You will just go through and make it with the simple steps what we have been discussed there. Okay. This will be that explanation of this algorithm, how the things will be moving in that algorithm. You just go through it. So